From the beautiful studios of Way Happy, this is Mr. Meyer and 3 increasing and decreasing functions in the first derivative test. But it's all kind of the same. It's like one is a graph decreasing, one is a graph increasing, and we kind of know a good way to tell, right? If you kind of just logically think about this, if a graph is decreasing like this, we know something about its slope. Its slope would be negative. And guess what? We know how to find slopes really well. We call it the derivative. Now, we also know how to tell when a graph is increasing because, again, we would talk about its slope. Its slope would be positive the entire time. So good news, this isn't going to scare us. So as you can see, as a function moves from the left, if it goes up, it's increasing, and if it goes down, we should say from left to right. If it goes up, it's increasing. If it goes down, it's decreasing. And so you can see over there that on that interval of the decreasing interval was from negative infinity all the way up to A, wherever A is. And then it was constant from A to B, and then it was increasing from B to infinity. And that's all that theorem 3.5 says. It says test the derivative. If you get a positive slope for your derivative, if you get a positive derivative, then you know the graph is increasing. If you get a negative derivative values, then you know it's decreasing. And if it's 0, you know it's constant, like we look for in the first 2 sections or something. So that feels pretty darn comfortable to me. All right, so here's my example 1. I give you guys this graph, and I say, you tell me when is it increasing or decreasing. And I should really look at this theorem a little bit closely too. It says that the function has to be continuous on the closed interval, and it has to be differentiable on the open interval. So that's kind of important, right? We know continuous. A lot of graphs, we know if they're continuous or not. We don't have to do too much work, but just think about the rules on domains that could hurt you, zeros and denominators, and square roots that have negatives under them, and logarithms that have zeros. And we haven't touched logs yet, so I'm not too worried, but logs that have zeros or negatives is the input. Then to see if it's differentiable, do those same rules, but do that with the derivative, right? So take the derivative and see if there's any of those rules that need to exist. So here we go. If I am going to find out when this graph is increasing or decreasing, it's got some steps, and you might remember these steps from really pre-calculus. So here we go. It says find the open intervals on which this thing is going. So it's open-ended, right? Now this is a John Travolta graph, right? It's got some stuff going on. It's probably got a turn in it, and a turn that we could describe probably 2. And that's what we're going to find out. So I know it's continuous, though. It's just a regular graph. There's nothing weird. No zeros and denominators, nothing. So I know it's continuous. So I can say continuity, check, right? Now let's talk about if it's differentiable. All right, if it's differentiable, then I should be able to find the derivative. So f prime of x is equal to, doing your derivative rules, 3x squared. Now bring the 2 out in front, and the 2's will cancel, and you'll get minus 3x. Now that's a parabola, and what I know from a parabola is it's continuous, right? And then I also know that it's differentiable. There's no weird corner points. There's nothing that ever gets me into trouble there. So I know it's differentiable. So differentiability, check. We're good. All right, now let's find out when this thing has a slope of 0. And those are our critical points that we learned before. So 3x squared minus 3x equals 0. Well, I'll factor out a 3x and be left with x minus 1, which means I have critical points at x equals 0 and x equals 1. Now, those are our critical points, right? That is when the graph has a slope of 0. I don't know what's going on either side, so I can't tell you if it's increasing or decreasing or whatever. So therefore, I'm going to draw this. It's got 0 and 1 as my critical points. So I'm going to fill those bad boys in, or at least mark them. And then I will test each side of this. Now, as I'm testing, I just want to see if it's positive or negative, because again, we are talking about the slopes. We're not talking about the actual function. All right, so let's look. Here is our beautiful function, and I'm going to plug in something smaller than 0. What's smaller than 0? Anything over here on the left. You could pick negative 10 for that matter. And if you do, you would get 3x times x minus 1. Remember, I'm plugging in negative 10. So I'm going to get a negative number out of here, negative 30 if you want. And I'm going to get a negative out of here, negative 11 if you care. When I multiply those together, I'm going to get a positive number. So all of these slopes are positive. All right, what about in between 0 and 1? In between 0 and 1, let's see. What's there? There's a half. Let's plug in a half. 3 times a half is going to be positive, and a half minus 1 is going to be negative. And when I multiply those together, I'm always going to get negatives. And last but not least, let's pick something bigger than 1. Let's pick a million. And when I plug in a million, I'm going to get 3 times a million, which is going to be positive. A million minus 1, which is going to be positive. Multiply those two numbers together, you get a positive. So as I did a check for each sign, I can see when the slopes are positive and when they are negative. Now, kind of this whole time, I've ignored this box to the right, which was silly of me, but it's kind of what we did. Step 1, we located the critical numbers, right? And that's what we did right there. Step 2 is determine the sign of each one in between the intervals, right? And that's what I did right here. And then, step 3 says, if you've completed that, I want you to use the 3.5 definition and describe if it's increasing or decreasing. Well, since the slope was positive, I know it was increasing on the interval negative infinity all the way up to 0. And by the way, it happened again at 1 all the way to infinity. Those were times when the graph was increasing. And the graph was decreasing from the interval, just that little chunk in the middle, 0 to 1. So that's how you can tell without even having a graph, without knowing anything. You can tell me when it's increasing or decreasing just by having the equation and looking at the derivative. And I didn't do too much work. That was kind of nice. All right, let me ask you a question. Let me show you that fancy vocab word right there. Monotonic. It's when the graph is increasing over its entire domain or decreasing over its entire domain. This one was not. It was increasing and decreasing and increasing again. All right, let me ask you a question, and I'll be right back. All right, nice work. Now let's talk about 3635. Told us when it was increasing and decreasing, and then 36 jumps along and says, hey, let's call it the first derivative test. Let's tell you if it's a maximum or a minimum. All right, it's not too bad. Again, same rules, right? It's got to be continuous. It's got to be differentiable. And then if it changes from, so if you're looking at a critical point and you look to one side, it's negative. Let's say from the left side, it's negative, and then it's right side, it's positive. So it's going from a negative to a positive. Well, you just found yourself a minimum. And let's say that it changes from a positive to a negative. Well, then guess what? You just found yourself a maximum. And if it's positive on both sides or negative on both sides, well, then guess what? You didn't find anything, right? And you can see the 4 graphs down below that I think are probably super helpful, super nice, and everyone will be happy when they read those. So let's look at my example 2 over here. Find the relative extrema for the function. So again, first off, is it continuous? Well, that's the graph of a sine graph, and I'm pretty sure we all know that sine graphs are continuous, so that's pretty good. So continuity, check. How about finding out if it's differentiable? So again, I'll find the derivative. So f prime of x is equal to, now if I have to find the derivative of this, the derivative of half is a half, or is 0, and the derivative of sine is cosine, so I have negative cosine of x. So boom, there is my derivative. Now, does the derivative of cosine ever give me something that is undefined? No, right? It's a nice smooth graph. So I know it is differential there, and I'm good for differentiability. Now, what about when the derivative is 0, right? Well, let's see. Will 0 ever equal negative cosine of x? Well, sure, right? You can get rid of the negative because it doesn't matter. And the cosine, when does cosine equal 0? Well, I'm pretty sure that that's pi over 2. So at pi over 2, or 90 degrees for the weird kids, that's when I would get a cosine of 0. Oh, wait, and there's another one, a reference angle of 90 degrees would also get you a 0. So that means 3 pi over 2, or 270 if you're still thinking about degrees. So there is your two areas on the interval 0 to 2 pi that will give you a derivative of 0. All right, let's check either side. Now, how do we do that? Just like before. So I got 0, and this is where we're starting from. And I got 2 pi here. This is where we're ending. And I got, pi over 2, so half a pi. So here's 1 pi, and then there's half a pi, not really in the middle, but that gives me a fit. And 3 pi over 2 gives me a fit, 1.5 pi's. So let's test things on the other parts of them. So as I go ahead and I do that, I'm going to test 0, right? So if I fold down 0, I'm going to say, all right, 0, I'm going to find the cosine. That's 1. And then the cosine is 1, and then put the negative on it. It makes it negative. Then I'm going to do pi, which also has a derivative of 0. And I'm sorry, also has a reference angle of 0. Find cosine, which is 1, but then because of the location of pi, all students take calculus. It's over here where cosine's all negative, so therefore it's negative. So the cosine of pi is a negative number. It's negative 1. And then I have a negative out front of that. It's going to make it positive. All right. And now let's do after 3 pi, let's do, I guess I shouldn't have done 0 because it was not including. I should have gone a little past or a little higher. So I should have done 30 degrees. So I guess same thing here. I should do not 2 pi. I should do 30 degrees shy of that because I can use my hand for that. So a reference angle of 30 degrees here, according to the all students take calculus, cosine is going to be positive. So what is the positive answer for cosine? It's root 3 over 2. But then make it negative. So it's going to be negative. So I've now checked, right? And if you go from left to right, like we said, you get a negative and a positive. That means you're going to get a relative minimum at pi over 2. And then look, at the next critical point, you go from positive to negative. Oh my gosh, that's a relative maximum at 3 pi over 2. Now let's go ahead and check that graph just if you're kind of curious. So remember, this was a sine graph right here that was up a half a unit, and it was a negative sine graph. So what does that mean? It means it was up half a unit. So that's our new midline, if you remember that. Here's 2 pi, here's pi. And if you remember how a sine graph went, it started its graph at the midline, and then at the first tick mark, we went up 1 whole tick mark, and then back at the midline at the next tick mark, and then we were at the next tick mark, we would be at the lowest point, and then back at the midline. And that's what our sine graph should have looked like. Oh, take it back. It was a negative sine, right? So it should have gone down at the first tick mark, and then midline, and then back up at the next tick mark. And this is what our graph would have looked like right here. And there's my sine graph from 0 to 2 pi. And if you notice, just like we said, we had a relative minimum at pi over 2, and we had a relative maximum at 1.5 pi's. So exactly what we were hoping for. That's it. Stay happy, and I'll see you tomorrow.